Once we know the definition of a function, we sometimes are asked, well, can you apply the definition? In other words, like in this case here, we've got this expression x squared plus 3y cubed plus 7 equals 0. And we want to know, does that, first of all, in this expression here, is y a function of x? Well, here's what you can do. Sometimes it's hard to tell by looking at it this way. But what you can do is just go ahead and solve for y. And what you get then is you get 3y cubed equals negative 7 minus x squared. Okay, that's what you get. And then you can divide by 3 and take the cube root. So you get y equals the cube root of negative x squared minus 7 over 3. Now, when you get a situation like that, notice when I've got y cubed equals something, I can just cube root both sides. And notice, every x I put in here, you just get one y out. That's because we were taking an odd root of this y. So when you get this situation, you say, well, yes, y is a function of x. See? Because if I put in an x here, I just get out one y. Now, contrast that down here where it says, is x a function of y? Well, solve for x. And you get x squared equals negative 7 minus 3y cubed. Okay, like that. And then you can square root it. Now remember, when you're solving an expression like this, I've got to do plus or minus. So this is plus or minus negative 7 minus 3y cubed. Well, now you can see there's every y that you put in, you get a positive and a negative output. So you get two outputs for one input. So is x a function of y? In other words, for every y, do you get exactly one x? And the answer is no. And you can see that because x was squared, and when you take the square root, you have to do the plus or minus. Okay, so there's an example of how you can be asked, does this expression represent a function of y in terms of x, x in terms of y? Okay, so now let's think about how we use the parent functions and these transformations to figure out what the graph looks like. So we've got this absolute value of x minus 3. Now, we immediately note, okay, well, this is just the parent function being shifted down 3. Or in other words, all the y's are being reduced by 3. So I'm going to just do a rough sketch of the parent function. Here's the absolute value. Okay, here's the absolute value. That's the parent function. That's if we didn't have any shifts at all. Okay. That's if we didn't have any shifts at all. Now, what we want to do is say, well, we have this vertical shift down, so all the y values are shifted down a unit, or 3 units. See, this vertex here goes down 1, 2, 3. And then nothing changes about the shape. This is called a rigid transformation. So, I need to just put that solid, don't I? There we go. There's the graph, okay? So I did this up here just to kind of give me a framework and then say, okay, well, I'm going to move this around. And this is what the graph looks like. Now, it was on the outside of the absolute value. Now, if it's on the inside, I'm going to do the opposite of what you would think. You would think, well, I'm going to move this to the left. No, you're moving it to the right. You can think of it as you're kind of having to move to the right to counteract this negative 3. So once again, we have, the basic absolute value, the parent function here. Here's the parent function. We're shifting to the right. So this point right here goes 1, 2, 3 over here. And then we can just sketch. There we go. So like that. And what this does, remember, this adds 3 to every x. This subtracts 3 from every y. Okay. Now, look at this one. This one's got 2 things going on. So we take the regular absolute value function that had a vertex here. So just think of the vertex. We've already kind of sketched it over here, but just think of the vertex. What's happening to this vertex? Well, it's going over 3, 1, 2, 3, and down 3, 1, 2, 3. So there it is, right there. And we can do our sketch from there. Okay. Just cuts right up through here, 45 degrees. I got kind of shaky there, the last part of it. But that's what it looks like. Okay. Any questions about that? I'm sorry for the graph. My space is kind of cramped here where I have the camera set up, so I get off a little bit there. But any questions about that? Okay. Now, let's go down here to the next one. Okay. Okay. So we've got a negative here. On the outside, that means that all the y's are going to have their values changed in sign, and the x is shifted. This is x plus 2, so everything is shifted to the left. So this point right here goes over to the left 2 units, and this tells me that all the y's have been, their signs have been changed. So it looks like this. There we go, like that. Okay, so there's what the graph looks like. We've turned the graph upside down and we've shifted it to the left. Or another way to think of it is all the y's have been multiplied by -1 and all the x's have had 2 subtracted from them. Okay, now this one, okay, once again, we've got a shift to the right 2 and up 3. But this time, what we're working with is the absolute value, the square root function. So let me go ahead and put, just put a rough graph of the parent function. The parent function is something like that, right? Absolute value. But this parent function is going to be turned upside down and raised up 3 and shift it to the left 2. So you turn it upside down and then you raise it up 3. So, and we're shifting to the right 2. So we go 1, 2, and then up 3. 1, 2, 3. But remember, it's upside down. So let me just put a little axis here. And, okay, so it looks something like this. Okay, just a rough sketch. Oh, no. I think I've... let me see here. 1, 2, 3. See, I'm getting bogged down here. Okay, something like this. Forgive me. Okay, but it's this graph shifted over, up, and turned upside down. So what happens to a point on here? For example, the square root of x has the point 1, 1. Okay, now what's happening to that point? Well, you're going to add 2 to the x. Well, what's happening to the y? You're multiplying it by -1, so you got -1, and then you're adding 3. Okay? You multiply by -1, and then you add 3. So we have now this point 3 and 2. So this point 1, 1 is now going to be over here 1, 2, 3, and up 2. So right there. Now my graph, I realize my graph is really bad, but anyway, hopefully it was good enough so that you see what's going on. Any questions? Okay, now let's look over here. Now this graph, okay, so sometimes it's difficult when you've got all these flips going on, but you see what's happening. This graph is going to be turned upside down and then reflected over into the x and then shifted up 3. Okay, so let's just think about, it might be easier for us just to think about, just to plot a couple of points. On the square root graph, we've got 1, 1 and 4, 2, right? The square root of 4 is 2. So let's think about what happens. The x is going to be changed to negative. The y is going to be changed to negative and then shifted up 3. Now the same thing over here for this one. The x is going to be changed to negative, and then the y is going to be made negative and then up 3. So let's see what points we have. We have these points. -1, comma 2, and we have -4. Let me make it where you can see that. -4, comma 1. Okay, so -1, 2. So there's -1, 2. There's a point on the graph. And then we've got -4, 1. Okay, something like that. Okay. Yeah. Yeah, I'm recording it. Yeah. Oh yeah, it's being recorded. So now the graph is going to go. Let's see here. Well, let's see. It's going to actually. I think it's going to go like this. Yeah, there it goes. Like that. Okay. Any questions about that? Okay, so on these ones, we're using the same principles. You know, we're talking about these transformations, but this time we're not given the equation or the function and asked to graph the function. We're given the graph and asked to find the function. So when you look at this, the first thing you think about, you're thinking in terms of parent functions. This looks like an absolute value function. And you can see it's got a, you know, that's just this v, and the slope is 1. See? Slope is 1, and that's the way absolute value function is. But normally you have a point here, and the function goes up this way, you know, the absolute value function. But what's happened, this point is no longer here, it's down here. So what's happened? Well, you've gone to the left, 1, 2, 2 to the left. So I'm going to do x plus 2. Got a horizontal shift there. And down 1, 2, 3. So there is the function. There's the model for this particular graph. Okay, now you go down to this one and you say, okay, I've got the square root here. This looks like a square root function. And in fact, it looks like the square root function that's been shifted to the right 2 units. So it's just going to be the square root of x minus 2. Everything else looks in order. Yeah. So if you go over 4, the square root of 4 is 2. So it looks like everything's just been shifted over 2 units to the right. Okay. Now this next one, this also looks like a square root function that has been turned upside down. And not only that, flipped into the, you know, across the y, right? So it looks like this is going to be negative the square root of negative x. Okay, so you've got this thing, it's been flipped over and then flipped over here and then shifted up 1, 2, 3, 4, plus 4. Okay, let's look at just a function here. We're given a function in terms of a graph. Okay, so we don't know, we've not been given the algebraic expression or anything. We're just told, okay, if this is the function of f of x, find f of x plus 2. Okay, so that means move everything over 2 units to the left. So this point right here, it goes 1, 2, 2 units to the left. This point right here, 2 units to the left. This point right here, 2 units to the left. And then just connect those points. And that's our, that's what effect this x plus 2 has. It just moves everything to the left 2 units. In other words, every x value has been decreased by 2. Now, let me just take note of some principal x values here, and we might refer to this later if we need it. We've got the point 0, 4, and we've got the point -4, 1, and we've got the point 4, 1. Now later on we may want to refer to those to help us to get our bearings, what the graph looks like. But we won't every time, I don't think. Or we didn't for those other two. Now look at this one. This point right here, let's just do a point at a time. We'll move 2 units over and then up 2. There. This one, 2 units over and up 2. This one, 2 units over and up 2. There, like that. See? 2 to the left and then 2 up. Now these are rigid shifts here. Rigid, rigid, rigid. Because I don't guess did I not sketch this one? I guess I left this one off, didn't I? Okay, so we're going up 2, and up 2. Sorry about that. Didn't mean to leave it off. Okay, there it goes. These are each what we call rigid shifts because they don't change the shape. The shape is not changed. We just move it around. We keep the exact same shape, but we move it around. Now down here, we've got rigid shifts. We've got 2f of x. Now remember what this 2 does. This 2, outside the function, we're going to multiply the y by that 2. So the x's don't change. We've got the point 0, 4. Well, this is going to be 0, 8. We had the point -4, 1. So this is going to be -4, 2. See, I'm just taking these y values and multiplying by 2. We have the point 4, 1. We're going to have the point 4 and 2. And now, if I plot these, I got 0, 8. There's that point. I've got -4, 2. There's that point. And 4, 2. So, there's what our graph looks like. A little steeper. Okay, now here's another non-rigid shift. We've got 2x. That means we're going to take all the x's and divide by 2. So we've got these representative points here. 0, 4, -4, 1, 4, 1. And what I'm going to do, since it's inside here with the x, I'm going to take the x's. 0 divided by 2 is 0. -4 divided by 2 is -2. 4 divided by 2 is 2. See, we do the opposite to the x's. And then these are not changing. See, the y's aren't changing. 4, 1, 1. So, and now I'm going to plot these points. We've got 0, 4. Okay, nothing's changed there. -2, 1. And 2, 1. So there's what it looks like. Okay. Now we come over here, and here's what I'm going to do on this one. I'm just going to go ahead and take note of these points. 0, 4. So here I've got these points. This is the f. So we've got, this is just f of x. We had 0, 4. We had -4, 1. And we had 4, 1. And I want to look at, well, what happens when we have -x plus 2 plus 1? Because there's a lot going on here. So here's what I want to do. As far as the x's go, I'm just going to subtract 2. See? All I did was took 2 away from each one of these x's. Now, as for the y's, I'm going to multiply by negative and then add 1. I do the multiplying first. See, here's negative 1 plus 1 and negative 1 plus 1 again. Okay, so there's our new points. There are our new points right there. So let's think about what they are. Negative 2, negative 3, negative 6, 0, and 2, 0. Okay, so let me go ahead and plot these. Negative 2, negative 3. So there's negative 2, 1, 2, 3. Okay, negative 6, 0. Negative 6, 0, and 2, 0. And here's what it looks like. So we shifted it to the left, turned it upside down, and shifted it up 1 unit. So, any questions about that? Okay, so we've got these 3 functions here, and we're going to look at how we set up the difference quotient for each one. Okay, so first of all, we've got the x plus h squared. See, I'm just going to rewrite this function, but every place I have an x, I'm going to put an x plus h. Now be careful to remember to put in the 6. That's a place where you could mess up because you're putting in an x plus h here and here. It's easy to forget the 6. And also, it's easy to forget to put this whole function inside the parentheses. Okay? So here's what we've got. Now remember, the difference quotient is f of x plus h minus f of x over h. So here's what we have. F of x plus h, that's this first part, minus f of x all over h. Now, what we do with a simple one like this, this quadratic function here, we multiply everything out. Now, another mistake that some people make is in multiplying this out, they'll call that x squared plus h squared. But train yourself not to think like that. This is x plus h times x plus h. And then we have 5x plus 5h. And don't forget the plus 6. Easy to forget that. I've done that lots of times. I've forgotten the constant there. And then you drop your parentheses. All over h. And what happens after you do this, is things start to cancel out. See? That's cool. And that has to happen. If that doesn't happen when you have a problem like this, probably you just made a sign error somewhere. Like, for example, if you forgot to change this positive 6 to a negative 6, it wouldn't cancel out. So you know at that point, I've done something wrong. I need to go back and check my work. Okay, I'm trying to squeeze all of this in. But there it goes. Now, you notice an h. You've got an h in each one of these. So I can factor out the h. Let me move this over a little bit. And here's what I get. I get h times 2x plus h plus 5. The h is canceled. Now, in this class, this is as far as we're going to go. When we've got that h divided out on the bottom, we're done. Now, later on, when you take calculus, you'll go further than this. But right now, this is as far as we want to go. Okay. Now, that's the first type. Now, you also have the difference quotient for this one. Okay. So we have x plus h plus 9 minus x plus 9, square root of x plus 9 over h. See? All I did was I just put in place of the x plus h plus 9 minus, so this is f of x plus h minus f of x all over h. Okay? Any questions about that? Okay? Now, the trick with this one is to multiply by the conjugate. So what I'm going to do is I'm going to multiply the top and the bottom by the conjugate of the top here. So this is going to be the square root of x plus h plus 9 plus the square root of x plus 9. And I'm going to do that same thing to the bottom. You can't just do it to the top. Okay? Now, when I do that, here's what happens. What we want it to happen was we know we want to cancel out this h on the bottom. We want to divide it out. But we can't at this point because the h is underneath the radical. But by multiplying by the conjugate, we get this. We get x plus h plus 9 minus parentheses x plus 9. Ah, there. It's out from under the radical because it's a difference of squares. You know, a plus b times a minus b is a squared minus b squared. And then we've got this thing. Okay. Now, at this point, we can things start to cancel because up top we've got x plus h plus 9 minus x minus 9. And on the bottom, we've got all this. There. And no need to try to multiply this out or anything. That would just, cause problems. Just leave the bottom the way it is. Now these x's cancel, these 9's cancel. Now you can see this h will cancel with this h, and we're done. So we've got the square root of x plus h plus 9 plus the square root of x plus 9. There we have it. And at that point, we're done with that problem. Okay. Now, let's look at this one. We've got 2 over x plus h plus 5. That's f of x plus h minus 2 over x plus 5 all over h. Now the trick, so up here the trick was multiply by the conjugate. The trick here is multiply by the common denominator. So what I'm going to do, the common denominator of x plus h plus 5 and x plus 5, so what I'm going to do is I'm going to multiply the top and the bottom by x plus 5 times x plus h plus 5. That's the trick. And there's nothing wrong with that because we're just multiplying by 1. See? X plus h plus 5 times x plus 5. Over that, over itself, that's just 1. See? This divided by this is 1. And then I distribute this through. So here's what it looks like. We've got 2 times x plus 5, x plus h plus 5 over x plus h plus 5. Okay? That's on this first term. So what I'm doing is I'm just multiplying this by the common denominator. Minus 2 times x plus 5, x plus h plus 5. All over the bottom, which is h times x plus 5. There, like that. Now this looks like a mess. So we quickly say, let's get this cleaned up. Some things divide out. That's what we wanted to happen. Because now it doesn't look like such a mess because we have 2 times x plus 5 minus 2 times x plus h plus 5. And then down here we have nothing's changed. There. Well, now, once we do that, we're on our way. There's nothing can stop us, except, little sign problems. Like, you got to be careful when you're clearing this parentheses to mind the negative out here. So you've got 2x plus 10 minus 2x minus 2h minus 10. Like that. And you can dig what happens here. These cancel. Cool. And it looks like you've just got negative 2h over h here. The h's will cancel. And you're done. You've got negative 2 over x plus 5, x plus h plus 5. And at that point, you've simplified the difference quotient as far as we're going to take it. Okay, as far as finding domains go, this kind of represents 3 types of problems that you could see. One, you've got a function with a variable, an independent variable in the denominator. Now, the question is, well, when we say what is the domain, we're saying what values can you let x be and still get a real valued output? That's what we're talking about here. Well, really, on this one, anything as long as x plus 3 does not equal 0. That's the thing. So in finding the domain, you're just trying to find out what's going to make this denominator 0. Well, as long as x does not equal negative 3, I'm good. So what you do is you find out what values for x will make the denominator 0, and then you exclude those from your domain. And this is the domain right here. Or you could say negative infinity to negative 3, negative 3 to infinity. Okay. This is kind of a cool way to write it, interval notation. Now with this one, your concern is not dividing by 0, but you want 2x plus 5 to always be greater than or equal to 0. So you just solve that. X greater than or equal to negative 5 halves. Or you could say negative 5 halves to infinity, using the cool interval notation. Okay, now over here we have a combination. We have, on the one hand, we want x plus 3 to be greater than or equal to 0 because of the radical there, the square root, the even index radical. And also we want that x minus 4, it can't equal 0. In other words, x cannot equal 4. So here's what we've got. This one up here gives us that x must be greater than or equal to negative 3. So our domain is this. X is greater than or equal to negative 3, but not 4. It can't be 4. So we could do this. We could say, okay, negative 3 to infinity normally. That's what we would put if we didn't have to take into consideration this 4. But instead we're going up to 4, jumping over it, and then going on to infinity. So starts at negative 3, goes to 4, jumps over 4, and picks it up on the other side and goes to infinity. Now, there are other types of domain problems that we've encountered at this point. For example, you could have a problem like this, 3 over the square root of x plus 1. Well, now this is kind of a combination where you've got a variable in the denominator and an even index radical. And when you have a situation like that, what you need to do is say, okay, normally with the radical I would say x plus 1 greater than or equal to 0. But I can't have it equal 0. So I just have it strictly greater than 0. So x has to be greater than -1. So you would have -1 to infinity. Okay. Okay, so we want to look at the inverse part of it. Now, I've got here just different types of functions where you would need to find the inverse. Now, remember the process. You change notation, interchange variables. Okay? So I change notation, I interchange variables, and now what I've got to do, and this is where the algebra comes in, you just got to solve for y. Now in this case right here, you've got y equals x minus 1 over 2. See? Subtract 1 and divide by 2, and then you can change notation back. There we go. And there's your inverse. Okay, down here, another one, we've got y equals x cubed plus 7, or writing the inverse, you would get x equals y cubed plus 7. Okay, so we interchange the x's and y's, and then we solve for y. So we get x minus 7 equals y cubed. Now to just have y equals, we cube root both sides. And when you cube root y cubed, you just get y. And then you have the cube root of x minus 7 on the other side. So what we have then is we have f inverse of x equals the cube root of x minus 7. Now, does anyone have any questions about that? Okay. Now we go to the next one. We have y equals the cube root of 2x plus 3. Now I'm going step by step here. You don't have to do this part. You can just immediately jump into, interchanging the variables and then solving for y. Now, so we've got to solve for y here. Y is underneath this cube root, so I need to cube both sides. So I get x cubed equals 2y plus 3. Subtract 3. And then divide by 2. So you get y equals x cubed minus 3 over 2. And that's your inverse right there. So you can put it back in function notation. Just to say, just to make it clear, this is the inverse of the function f. Okay, now for these ones down here, sometimes this is gives people a little more trouble. Notice you've got y equals x plus 4 over x plus 5. Now I want to interchange the variables. So I get x equals y plus 4, y plus 5. Now the process here, you want to solve for y. A good first step is to multiply both sides by y plus 5. Because when you do that, look what happens. This is just good equation solving strategy. You got y plus 5 here, and you multiply by y plus 5. Okay. What's good about that is that these cancel out. And it causes us problem trying to solve for y, and it's trapped in the denominator. So we have to liberate it. So now we have xy plus 5x equals y plus 4. Like that. I'm going to factor out a y. Whoops, not yet. Let's don't factor out a y yet. I'm sorry. Got ahead of myself a little bit. I need to gather my y's together on one side first and move the x's to the other. So we've got xy minus y equals 4 minus 5x. Now I can factor out a y because I can't combine these in any way, but I can factor out a y. And get that. Then just divide by y, by x minus 1. Yeah, like that. Okay. So that's the process. Now, I put a little more complex one here just because, it just adds a level of complexity because we've got the coefficients here. But we would start off like this. We would say 3y plus 2 over 2y minus 5. Multiply both sides by 2y minus 5, and we end up with this. Okay, so I kind of skipped a step there. But you can see what I did was I just multiplied both sides by 2y minus 5. And the 2y minus 5 cancel out over here. And now I clear my parentheses, so I've got 2xy minus 5x equals 3y plus 2. Now I want to gather my y's together. 2xy minus 3y equals 5x plus 2. Now I factor out the y. And divide. Yeah, that's it. That's it. That's the inverse right there. To show these functions are inverses of each other, we need to show this. F of g of x equals g of f of x equals x. So we start off. We say, okay, here is f of g of x. So we have 2 blank plus 7. And what I'm going to put in there for the blank is the g of x. Okay, so that's going to be x minus 7 plus 7, which equals x. So that's the first part of what we want to show, f of g of x. Then we go back and say g of f of x. Okay, so this is going to be g of x. See, I just write x minus 7 over 2, but in place of the x, I put a blank, and I put in a 2x plus 7. Now what we want to do here is we want to simplify the top first. And you'll notice this is 2x over 2 equals x. So, yeah, f of g of x and g of f of x are both equal to x. So, yes, these two functions are inverses of each other. Okay, so let's look at these combinations of functions here. We've got f of x and g of x. We want to be able to find things like this, f plus g of x. Well, this literally, it's just really just notation. It's just a shorthand to write f of x plus g of x, and that's just going to be 2x plus 3 plus x squared plus 2x. Yeah. So this is really x squared plus 4x plus 3. That's all there is to that. Now, you have to be careful if this were f minus g, because remember, if it's minus, I would need to put this whole thing in parentheses. So you can get messed up there with your signs if you're not careful. Now this one, this is just multiplying the two functions together. Yeah, like this. Just multiplying. And remember, we just distribute. Just distributivity going on here. So we've got 2x cubed plus 4x squared. And then I distribute the 3 through, plus 3x squared plus 6x. Yeah, there it goes. So let's see what we got here. We've got 2x cubed. Check that off. 7x squared plus 6x. Yeah, there's all that. Okay. Okay. Now let's mosey on down to this one. This just means f of x over g of x. So we've got 2x plus 3 over x squared plus 2x. Yeah. And that's really all we need to do with that one. Now, you could be asked, well, what is the domain of that? Well, the domain is x squared plus 2x can't be 0, right? Well, you can figure out, now, at this point, we really haven't devoted any attention to solving quadratic equations. That's in the next unit. But you could solve this thing right here, this, by just setting it equal to 0 and then factoring out an x. And you've probably seen this before, in your previous work with algebra, that this means that x equals 0 or x equals -2. In other words, if I allow x to be either one of those, that would make the denominator 0. So what I have to do for the domain is I could just say, well, x is not equal to 0 and it's not equal to -2. I could put those in there like that. Or I could use interval notation. The interval notation would go -infinity to -2, -2 to 0, and then 0 to infinity. So if we were asked for that domain, it would look something like that. Okay. Now down here is where we have these combinations of functions, but instead of having an algebraic expression, we were given the graph of the function. So here we have f of x, and here we have g of x. And we're asked, okay, let's find f of plus g of 3. Well, let's find f of 3 first. F of 3, let's see here. Looks like it's going to be 4. See, I just find it here on the graph. So that's 4. And let's find out what g of 3 is. Well, g of 3 is 2. See, I go over to 3 and I say, okay, up on the graph, that's 2. So this is going to be 4 plus 2 is 6. Now here is f times g of 3. Well, that just means 4 times 2. Right? Because we already found out what f of 3 is and what g of 3 is. So we don't have to do that again. We've got the numbers right here. Now over here, f of g of 8. Okay, so I've got to, now this notation we've not worked with very much, but this is it just means this, f of g of 8. Well, I need to find out what g of 8 is. So I go down here, there's 8, 1, 2, 3, 4. So this is f of 4. Okay, because g of 8 is 4. Now I need to figure out what f of 4 is. So I come over here to 4, and I look up here. Looks like it's 6. So f of 4 is equal to 6, and you're done with that one.